Hello, in this video, we're going to walk through another example from chapter 1 of EOPL 3. The code can be found in this GitHub repository. I'm going to go to chapter 1 and click on occurs free. So here is another example of a recursive program that process recursive data. So what we're going to process is some data like a scheme list, but it represents sentences in a language called lambda calculus, right? So the program looks like a scheme list, and then but it represents programs in this lambda calculus. So we're going to look at the grammar and then see how it's recursively defined and how we can create a recursive program to do something quite useful, which is to test whether a variable occurs free in this expression or not. Okay, so we're going to follow the grammar because that's really important. So this is the grammar definition. So we have one non-terminal, one syntactic category, right? So everything is we're dealing with lambda calculus expressions, valid lambda calculus expressions. So this category consists of three alternatives. So a identifier can be a lambda calculus expression. So in our program, it's just any quoted symbol, any symbol. It can be by itself as a valid expression. Or the second alternative, it looks like a lambda, okay, in scheme, but it's really the lambda calculus syntax. So it's used the same keyword lambda in parentheses, and then followed by a single parameter, which is identifier, can be an identifier, has to be an identifier in parentheses, and then another lambda calculus expression as its body. So as you can see, it's recursively defined. The non-terminal appears on the right-hand side. And then the third alternative is just a application expression, right? So we have lambda calculus expression, can be any one of the three, and then the body, the second element is the same. No, it's similarly any valid lambda calculus expression. So this is a definition of the grammar of this language, right? So we're going to see this is actually quite powerful as is, but in this problem, we're just going to do a simple task. But this is the grammar. This is the kind of data we need to process, right? So our program called occurs free is gonna take a symbol and then try to look it up in a quoted list. So this is the expression, lambda calculus expression, and then decide whether it's true or not, false. This variable appears free in the expression. Okay, so since we're gonna follow the grammar, I think yeah. So here it defines what we mean by occurs free. So if we have a lambda expression in the lambda calculus like this, so this x is bound, is called bound because this is declared as a formal parameter, right? So this declaration captures the occurrence of the variable in the body. So wherever in the body you use x, it refers to this x, whatever parameter we're going to get, actual parameter we're going to get, right? So it is bound, its meaning is clear, it will get its value when this lambda, this procedure is applied, right? So that's what we mean by bound. On the other hand, if like in this example, we have a x 3 times, right? So this is a declaration. So this x is bound to this x, right? Because it's a lambda expression. The body x refers to the parameter x. But then this lambda expression is used in another expression, an outer expression. In this outer expression, we have lambda calculus expression, another lambda calculus expression. So this is a symbol. We assume there's a procedure declared. This is subtraction procedure is already defined. But in this case, x is bound in this sub-expression, but is actually free in this expression, right? So x is not bound. So if we try to evaluate this expression, we'll need to find the meaning of x, the definition of x outside of this expression, right? It's not clear what this x means. So it is called free. So the last occurrence is free. So it's not bound by any so it's not bound by any of the declarations we have. Okay, we can see, right? So this is the problem we're trying to solve. We have some test cases, like for example, in this expression x, this is the case number 1, right? We have expression which is identifier, and it happens to be the same as the symbol we're looking for. So it is free in this expression, occurs free because we don't have lambda at all, right? So x appears not free. Well, actually this does not it's not apply really, because in the expression this is a simplest lambda calculus expression which is identifier by itself, and it's not what we're looking for. So is x free? Yeah, if it's the same, it's free. If it's not the same, we say it's false, right? So it doesn't really apply, but we return false. Okay, in this case, this is the second second alternative, right? We're looking at one of the lambda calculus expressions, which is lambda expression. Now, start with lambda with a variable parameter declaration, and it matches this, and so all the occurrences in the body are not free because they're bound to this declaration, right? So the answer is false, right? So if x equals to, if it's lambda expression, the parameter equals to what we're looking for, and x cannot be free in this in this expression, right? In the body, if it appears in the body, it's not free. So here's another one. So x, we're looking at a lambda expression as a lambda calculus expression, second alternative, and the parameter is not x, not what we're looking for. We're looking at, and then it's not going to be free because it's going to be free because it cannot be bound to the formal parameter because the formal parameter is different, right? Okay, so now here's a more complex, the third alternative, right? So we're looking at an expression, lambda calculus expression is a third kind because it is not lambda, it's not identifier, it is two lambda calculus expressions put in as a pair or in a list. So then the question is, so then lambda occurs free in this overall expression if it occurs free in either one, this one or that one. So does x occur free in this expression? The answer is no, because we have a rule says if this the symbol we're looking at is the same as the form parameter, it cannot be free. But it's free here because we have this alternative, and then actually to test whether x occurs free in this expression or not, we had to look at both sub-expressions. X occurs free in this sub-expression if it occurs free in this expression or in this expression, right? We have seen before x occurs free in this expression of an identifier by itself, right? So the whole thing returns true. So here's another more complex example. So we have lambda expression, but inside its body is another lambda expression, because as you can see in the grammar definition, the body of the lambda can be any lambda calculus expression. right? So we're going to run our test recursively. So this doesn't match that, so whether x occurs free in this overall expression depends on whether x occurs free in this expression. Well, it's a lambda again. The parameter doesn't match what we're looking at, so the answer depends on whether x occurs free in this expression. Well, this is the third alternative, a third kind of expression, lambda calculus expression. So whether x occurs free in this depends on whether x occurs free in this sub-expression or in this sub-expression, right? Since x occurs free in this sub-expression, so x occurs free in the overall expression, right? So these are the some test cases we're going to run to verify that our solution is indeed correct. So so the rules can be summarized as this. So we're following the grammar, right? There's only three possibilities, three possible things we need to evaluate, we need to analyze. So in the first one, if the expression e, which is the right hand side, is a variable, then the variable x occurs free in e if and only if x is the same as e, right? If it's the same, it's free. If it's not the same, it's false, because it's if and only if. So the second case, if e is in the form of lambda y e, then the variable x occurs free in this whole expression if and only if y is different from x and x occurs free in e prime, right? So if y is equal to x, then the answer is clear, it's not free, because it doesn't matter where x occurs in this sub-expression, the body expression, it's bound to this definition, right? So that's the rule for second case. Okay, here's the rule for the third case, right? A lambda calculus expression can be a lambda calculus expression and another lambda calculus expression in a list. So then the answer is that depends on whether x occurs free in E1, the first sub-expression, or the second sub-expression. So either or both, right? So now this is the summary of the rules, and we're going to write a program that can test this condition and do it recursively, so it always gives us the correct answer. Okay, so I'm going to copy, here's the code. I'm going to copy it and paste it to my editor. I'm going to run it. We're going to read it and then run some test cases. So I'm going to get the tracing off first. Okay, so we're really following the grammar strictly, directly. So we call it occur free. It's a lambda. It's a procedure. It takes two parameters. First is a variable as a scheme symbol, and expression, right? So if the expression is a symbol, it's an identifier, then the answer depends on whether the variable equals to the expression. Second case, if the first element, the car of the expression, is okay, so it's not a symbol, right? It has to be a list. If the first element is a symbol lambda, that means it's a lambda expression. Now, whether var occurs free in exp or not depends depends on this condition, right? So it occurs free if the variable is not the parameter of the lambda expression. Okay, it's used the combination of the car of the curter, and it's not that, and also occurs free in the body of the expression. So I'm gonna actually run an example for you to show you. So okay, so I have that. I'm gonna copy this, and then I'm gonna just practice so car. So now, okay, so since the program we have we're processing as a piece of data, we're actually treating a program as a piece of data. Since it looks like a scheme list, we can treat it as such, right? So if it is a lambda, something like this. So if ask for the car of this list. It's going to give us the first element, right? Now, how do we get this? Well, this is the second element, but itself looks like a list, and X happened to be the first element in the list. So what we can do is we can get the curter. Okay, let's see, curter is going to give us everything but the first element, right? So that's the curter, the remainder of the list. Now, after that, we can get the car of the curter. So this is a shorthand for car followed by curter, right? So okay, I'm gonna run it once, and then we could write the same as that. So I'm gonna use car followed by a curter. So that gives us the same thing. So we use catter, okay? So we use catter. So that gives us S. Well, now if we want to X the formal parameter of this program, we can just do another car after the car of the curter, right? So that gives us that. So that's why the cadr, CAADR express give us the formal parameter. Make sense? Okay, so now that's that. So then the car of the curter, let's see. What is, okay, let's start with the curter. We're gonna extract the body, which is one the body. Okay, how do we get that? Well, it's not the first list. It's not the first element. It's not the second element. So we need to get rid of both of them. So we do curter twice. Okay, curter once, get rid of the first element, give us the remainder. If you do a curter again, apply curter again, that's going to get rid of the second element. So we have the rest of the list as a list, right? Everything, the rest of the list. Now what we need is what's inside the list, right? The first element in the inside list. So what we do is we do a car after that, so that gives us that. So that's why the caddr give us the body of the lambda expression. So that's the second case, right? Okay, so now the third case. Here's a grammar. If it's not an identifier, a symbol by itself, or if it's not a list that starts with lambda, it has to be this, right? We assume the expression is valid. So now, according to the rule, we'll have to recursively look into both of them to see whether the variable occurs free in either one of them. So now let's look at the code. So this is we just program as such, right? We use else for cons, and we use or to connect these two cases. So car of the expression, yeah, let's do this. I'm gonna show you the example. So if, yeah, let's look at this. So this is an example of a third alternative, right? So it looks like this. It has the expression followed by another expression, right? So now let's see. Of course, if we do car, that gives us the first one, right? That's what we want. But how do we get the body? The second one. Sorry. Yeah, the second one. So this is the first one. Actually, yeah, that's the first one. That's the second one, right? To get the second one, we need to car of the curter, right? We do curter first, and then we do the car. So that gives us the second element in the list, right? So that's why we can write a program like this. Okay, so we call occurs free on this first sublist, then call occurs free on the catter of the expression, which is the second element in the list, and we use or to connect them. So this, as you can see, looks complex, but we were able to write it clearly and be pretty confident that this works because we have implemented according to the rules by following the grammar, right? So it has to work. It's recursively well formed. Now let's run it and see the result. I'm gonna run a couple examples and I'm gonna do some trace. Okay, so this is pretty straightforward. Oops, I should need to copy the result. just the code. Okay, so that should give us true, and then just run this one. Have some confidence. Okay, this is also true. Let's do some tracing. Okay, so yeah, let's do this one. Okay, gonna comment this out. So I'm gonna trace this procedure. So we call that, and then since x, this is the second case, since the car, the parameter for the lambda is the same as the variable, it's not the same, it's the same as the variable, then this and is a false, right? And false with anything is false. So we know the answer is true, it's false, so x does not occur free in this expression, which is correct. Okay, so now let's look at this example. Okay, this one gives us true because it's still the second alternative form of the program. So this is a piece of data, which is our program, lambda calculus expression. And then because it's a lambda, and then the variable x is not the same as the parameter y, right? So then whether the answer depends on whether the variable occurs free in the body, right? That's what we're the correct logic. And then so we call occurs free on the apply that to x and the body of the lambda, right? So now we hit the third case. It's occurs free. We call occurs free recursively. It's not an identifier. It's not a lambda. It has to be this, right? Then we recursively call occur free, apply it to a variable and the car of the expression, which is x. So now we're back to the first case. It's a symbol and they're equal, right? The expression is the variable itself. Then the answer is true. It occurs free. It's not bound to any definition in the expression, so this is true. Okay, and then now let's run one more, the last one. Occurs free. So now we have the first of all, it's overall it's a lambda expression, right? So we call occurs free on this lambda expression. Since x is not equal to y, according to the rule, the answer depends on whether x occurs free in the body of the lambda or not, right? So we call occurs free on the lambda, apply to a lambda, x and lambda. Well, then x is not equal to z. So whether x occurs free in this lambda depends on whether x occurs free in the body, right? So we recursively call occurs free, and now this is a third alternative form. So x occurs free if it occurs free in this expression, sub-expression, or in this sub-expression. So it turned out that it occurs free in this first sub-expression, so we can conclude that x occurs free in the overall expression, right? So this is a pretty good example to illustrate this principle that when we let's see, it's from the textbook. It's called the follow the grammar principle, right? It says when defining a procedure that operates on inductively defined data, the structure of the program should be patterned after the structure of the data. So our data is lambda calculus expressions, and our program has the exact shape, right? It's strictly defined by following the grammar itself. Okay, that's it. I hope this is helpful to you.